19, 7, 21, 7, 22, 7, 23, 7, 24, 7, 29, and 7, 31. These are all problems on probability of error calculations. They're all relatively similar. Kind of helps you exercise that equation that we derived about derived on pulse amplitude modulation about power. Okay, so let's continue. What we've done so far is we've treated AWGN. We assume that our channel is AWGN. What is special about AWGN? Two things. First one is the type of the noise, right? We are dealing with additive white Gaussian noise, with along with all the properties that come with that kind of noise. The second thing about AWGN is the fact that the bandwidth is unlimited. We didn't worry about the fact that your pulse may be of an infinite bandwidth. Let's say you can signal with a square pulse, and the square pulse comes out of the channel, just corrupted with some noise. That's not the case in majority of communication systems. Actually, it's not the case in any communication system. We're always dealing with some band-limited channel. Now, the limit may come for two reasons. One, the channel itself may be band-limited. Remember, at the very beginning, we talked about some of the wireline channels, and we said if you have a twisted pair, you can have 100 kilohertz of the bandwidth, and then after that, the channel becomes kind of like a low-pass filter. So the channel itself might be limited. But there's another reason why we actually may want to signal over a limited portion of the spectrum, even if the channel is of the wider bandwidth. And this is multiple access, right? Let's say if you have multiple communications that are sharing the same channel, the most efficient way to do that, or the most basic way to do that, is to actually give a portion of the channel in frequency domain to each one of the communications. And that's our FDMA access. And in FDMA access, you kind of say, okay, my communication is just going to use this portion of the spectrum. And we know that a lot of systems use FDMA access, even if, let's say, actually all wireless systems are, FDMA to begin with, because they all operate in a certain portion of the spectrum. And then also we have FDMA access on a landline channels as well. So what we're going to tackle, over these two lectures is just like how do you communicate over band-limited channel. In other words, what do you need to do to make sure that your signal goes through band-limited channel? And let's start by model of that communication. So model. Let's see if I find this one. Model of a band. That's what I was actually looking through this one. Can you see this? It's very faint.
Model of a band limited channel.
Huh? It's a coloring.
We have a black, Dr.
Have a blue. You have? Oh, look at my students. Which one?
Whichever.
All right, so one of them has to work. So here's what we're doing in this case. You have your SM of t. That's one of the symbols from your constellation that you're sending on a channel, right? It's one of the symbols where M is from some set 1, 2, up to capital N. But now instead of going through a channel that's not frequency selective, you have a channel that acts like some sort of filter. And this is C of t, where C of t is impulse response of the channel. You know, this channel, you know, would typically attenuate your signal, but what is important here, it will perform a filtering on the signal, so it will not treat all the components in your signal the same way. Now, at the output of this channel, you're going to still have your Gaussian noise, N of t, and then you have the receiver. And the receiver needs to do the same things we already talked about. It needs to demodulate and then detect, right? It will consist of demodulator and detector. And since this is a basic course, we're still going to treat those two separately. We're going to say first demodulate, and then based on what came out of the demodulator, we're going to make a decision about what has happened, what has been sent. Now that's the settings. Now to understand this better, what I do is, let me go through a simple example. And what the goal of this example is, what I would like to do is give you an intuitive feel. What happens as a result of this channel being band limited, right? What is the consequence of that, right? And what I'm going to do is I'm going to assume that this Sm of t is a square pulse, and that this is a low-pass filter. And let's see what happens at the output of this channel as a result of all this being a low-pass filter. So this is an illustration of a band-limited transmission. So here is our example. Sm of t is going to be equal to A times pi t over capital T. So this is essentially A for t smaller than t over 2 and 0 otherwise. So I'm trying to send a square pulse. It's a good pulse to send in this example because it's as you know, rich in the frequency domain. So, you know, the only way you can preserve square pulse is to have an infinite bandwidth. As soon as you start shrinking the bandwidth, your pulse is going to start changing. Now, what I'm going to say that C of f, which is my Fourier transform of C of t, if C of t is an impulse response, what is C of f? Frequency response of the channel, associated frequency response. And I'm going to say that this guy is equal pi f over c e to the minus j 2 pi f t 0. So it is an ideal low-pass filter, right? It has a bandwidth of WC, and it has a delay of T0. It has a constant magnitude, and it has a linear phase. Remember, ideal transmission system is the system with a constant magnitude and a linear phase. All that it will do, if you fit within a bandwidth of this filter, then what will come out of this filter is your signal delayed in time. How large is the delay? It's going to be delayed by T0. The problem is the pulse does not fit in any low-pass filter because its spectral content is infinite. So now I can treat this whole problem in a frequency domain. So let's say in frequency domain. We start by Sm of t is equal to A pi over t over capital T. Well, Sm of f, which is the Fourier transform of Sm of t. If my time domain signal is a square pulse, what is the frequency domain? It is going to be sync, right? So it's going to be sync associated with this pulse. And this is A t times sync of Tf. Right? One remark in passing, note that your book, the Proakis book that we're using, defines sync differently than your linear systems book. Remember, in linear systems, sync was sine x over x. Here, the sync is sine pi x over pi x. Right? There's that pi. So otherwise, you know, in linear system book, there will be a pi here, right, in front of Tn. So now, since I know Sm of f, what is my output? How do I call this output here? S out of t. Therefore, yeah, exactly. S0 of f is going to be your C of f times Sm of f. That's our beautiful convolutional theorem that says that the convolution in the time domain becomes a product in the frequency domain. Right? So in our case, this becomes AT sync of Tf times pi of f over Wc e to the minus j 2 pi f t 0. So that's what comes as the output of the filter. Now to get this actual S0 of t, what I have to do is to take inverse Fourier transform of this. So S output of t is going to be inverse Fourier transform of S output of f, which in our case becomes integral from f goes from minus infinity to plus infinity. I have to put this in here. So this becomes AT sync ft times pi f over Wc e to the minus j 2 pi ft0. And then I have e to the plus j 2 pi f t df. Right? It looks bad, but it's actually just straightforward. This is your here input signal. This is your filter, and then you're taking the inverse Fourier transform by appending the kernel and taking the transmission, taking the integration. Now this simplifies somewhat. So this is AT outside. Now this pi here actually controls the integration boundaries, right? It will be 1 when f is smaller than Wc in magnitude, and 0 otherwise. So therefore, integration outside of Wc gives you all zeros. So this becomes an integral when f goes from minus Wc to plus Wc, and then you have sync of ft e to the plus j 2 pi f t minus t0, here's the delay, df. Okay? Now, let me ask you this. This sync, what kind of function is this? Is this an even, odd function? Even function. So if I integrate even function in symmetrical borders, actually, so this is an even function. How about this exponential? Is it even or odd? It's neither. It has an even part and it has an odd part. So we can we actually can separate this into even and odd part, and then even times even gives me even again. Even times odd gives me odd. So that one goes away because I'm integrating in symmetrical borders. So let me just step through what I just explained. So this is AT integral when f goes from minus Wc plus Wc sync ft times cosine 2 pi f t minus t0 plus j sine of 2 pi f f t minus t0. That terminates sine, and then this is this guy, and then df. So that's what I need to evaluate. But you see right away that this splits into two integrals. The first one is an even function times even function. That one makes sense in symmetrical borders. The other one is even times odd, which is an odd function. And when you integrate an odd function in symmetrical borders, you end up with 0. So this ends up being AT, and then 2 integral when f goes from 0 to wc. And then I have sine of pi ft divided by pi ft times cosine of 2 pi f t minus t0 df. Okay. So this is what comes at the output of this filter. Now, sine times cosine can be decomposed using trig identities into sine of sum minus sine of the difference. So let me write that. I'll start. So as output of t becomes AT, this 2 here gets absorbed by 1/2 sine of the sum minus 1/2 sine of the difference. So it is 0. F goes from 0 to WC. And then you have sine of 2 pi F t minus t0 minus t over 2 divided by pi tf df, and then minus, put the integral when f goes from 0 to wc, sine of 2 pi f t minus, actually it is plus here, t0 minus t over 2 divided by pi capital Tf df. Okay? So I have these two integrals. Now I'm going to introduce substitution. For the first integral, x is equal to 2 pi f t minus t0 plus t over 2. And then for the second integral, I'm going to introduce substitution. X is equal to 2 pi f t minus t0 minus t over 2. In both cases, you see that df is equal to dx over 2 pi times this stuff, t minus t0 plus t over 2, and in this case df is equal to dx over 2 pi t minus t0 minus t over 2. So when I introduce those two substitutions, here's what I get. S0 of t is equal. Now this is just a couple more lines, and then it becomes quite neat. AT, now integral. When f goes from 0, where is x? 0. When f is equal to wc, so x is 2 pi wc of this. So this is 2 pi wc t minus t0 plus t over 2. And then I have sine of x. And then look what happens downstairs. I have, instead of f here, I have x divided by 2 pi t minus t0 minus t over 2. And then I have pi times t, these two. And then df is equal to dx over 2 pi t minus t0 plus t over 2. So you can see that these two guys are going to cancel each other. And then here I have minus integral when f goes from 0 to when f is equal to wc, this becomes 2 pi f t minus t0 minus, 2 pi wc. wc t over 2, and then sine of x divided by x over 2 pi t minus t0 minus t over 2 t times pi df over 2 pi t minus t0 minus t over 2. A little bit messy, but you know, you can see right away this cancels, and close the curly bracket here, and this becomes at. Now this is actually t and t cancels, and pi comes outside, so this becomes a over pi. And then I have integral from 0 to 2 pi wc t minus t0 plus t over 2 of sine of x divided by x dx minus integral from 0 to 2 pi wc t minus t0 minus t over 2 sine of x by x dx. Now this function here is essentially integral under the area under the sink, right? And this is a known function in math.
The second, is that dx on the second expression after the minus sign?
Yeah, of course.
And it's x equal, right, on the integral, lower bound?
Yeah, x goes. Thank you. And it's also here, x goes from 0 to that. Now, we define a function which is called sine integral, SI, as of z is integral from 0 to z sine of x dx. This is integral sine. That one doesn't have a closed form, but that's why we define the function that we call that way. So now, if you use this notation, then our output becomes over this form. So S output of t becomes a over pi, and then Si of 2 pi wc t t minus t0 plus t over 2, and then minus Si 2 pi wc t minus t0 minus t over 2. Right? And then really, what does this t0 do? T0 is the delay introduced by the filter. So in terms of shape of my pulse that comes in the output, T0 doesn't change anything. It just changes how far to the right this pulse is going to be. How much is the delay through the whole system. So, you know, to simplify, let T0 equal 0. Then your S output of T becomes A over pi SI of 2 pi WC capital T, and then this is T over capital T plus 1/2 minus SI 2 pi WC capital T, T over capital T minus 1/2. All right, so that's the mathematical formulation. Let's just understand what does this mean. First, let me draw the graph of SI of T. SI of T, right? That's the integral area under the curve for between 0 and T underneath the sink. So SI of T looks somewhat like this. This is axis T. This is 0. And this thing is pi over 2 minus pi over 2. And it kind of looks like this. So this is how SI of T looks like. So what we have here, we have SI shifted to the left minus SI shifted to the right. So if I were to draw this, here's how this S output of T looks like using this SI of T. So this is T. Let me just, this is minus 1/2. This is 1/2. So this is square pulse. This is what I have been sending, right? And what I'm going to draw here is what this output, S output of T, looks like for various values of WCT. If WCT is equal to 5, then here's how this guy looks like. I'm going to try to draw what I have here. Right? So this is for WCT equal to 5, or WC is equal to 5 times 1 over T. Right? Maybe I exaggerated this too much. It doesn't go this high or this low. Somewhat like this. It's not ideal, but we'll look into. Now, WCT equal 1. Here's how it looks. It needs to be symmetric, so which is not easy for me to accomplish on the board. So this part here is WCT equal 1, or WC is equal 1 over T. And now I have the last one. This here is WCT is equal 1 over 5, or WC is equal to 1 over 5. All right, so let's stop for a while and appreciate what is it that we derived here. This is ugly as can be. Right? I'm going to count your imagination. So, here's what we are sending. This is our channel. I'm sending here a square pulse. And the duration of the pulse is capital T. And I'm looking at the bandwidth here as a function of 1 over T. Right? 1 over T. If my bandwidth is relatively large, 5 times 1 over T, what comes output is is a very localized pulse, right? It has some ripple here, but it actually falls right off and it kind of dies quickly. So my pulse still occupies pretty much what it used to occupy. There is no dispersion in the time domain. It used to start with this here is T over capital T. So it used to start as being of a duration T, and it kind of ends up being the same duration. There's some ripple to the other side, but that ripple dies very fast. How do you explain that intuitively? Your bandwidth is relatively large. 1 over T is the first null of your sink, right? First null for the Fourier transform of this pulse. Remember, the Fourier transform of the square pulse is sink. 1 over T is the first null. So you're letting 5 nulls go through. So pretty much your entire spectrum goes through. So your pulse is very much preserved. It kind of ripples somewhat, but it dies, and it kind of does not pollute the adjacent bits, adjacent portions of the time. Now, as your WCT becomes 1, which means your bandwidth is essentially equal to 1 over T. Just you're letting the main lobe of your sink go through. What happens is this gets rounded, and it actually gets more dispersed in time, right? So it gets wider on each side. It's kind of not very easy to draw, right? So this is for WC equal to 1. So your pulse is not square anymore. It becomes round. Why? Because you cut out all the high frequencies that made it square in the first place. Remember, those sharp edges in your signal are made out of high frequency components. They're the ones that are fine building blocks that allow you to create those edges. If your filter has a bandwidth that cuts off those edges, then your signal becomes round. Finally, if your WCT is equal 1 over 5, which means the bandwidth of your filter is much smaller than 1 over T. T is the duration of the pulse. You can hardly see that there is a pulse. There is just this blur of energy that is distributed across many adjacent intervals of the duration T. This is a single pulse. Remember what we're doing. In most communication systems, let's say in the simplest way, you're going to use this, for example, to indicate 0, and you're going to use the opposite one to indicate 1, right? So you're going to be the signaling with plus or minus. So what happens as your bandwidth is small, or as it shrinks relative to the duration of your pulse now, energy of your pulse gets spread over multiple pulse durations. And this pulse here, which ideally should be between -1/2 and 1/2, now exists before and after, right? And what that does, it corrupts the adjacent symbols. How do we call this? We call this intersymbol interference. Because this symbol here, because of its dispersion in time domain, interferes with this symbol and interferes with the previous one, right? So now, if you look at what happens in band-limited systems, forget about noise. I'm my own worst enemy, right? Because noise is probably, let's say, even if I increase this power to the point where its noise, signal-to-noise ratio is really good, your signal is strong, and noise is very weak. The fact is that you're interfering with yourself. This bit here affects the next one, and the one after that, and maybe potentially several bits to the left and to the right. So the consequence of a band-limited transmission is this dispersion in the time domain, and the fact that now your transmission in a time interval of a duration t now results in the energy that is spread over multiple t in the time domain. And the smaller the bandwidth relative to the inverse of your bit duration or symbol duration, the larger dispersion in the time domain becomes. Okay? So now we see what is the fundamental thing that we're fighting with here? It's self-interference, self-induced interference. If you make an attempt to signal over band-limited channel without judiciously choosing your symbols or the waveforms that you're sending, you'll end up interfering with yourself. And no amount of power that you pump into the system or it will fix that. Because whatever increases the power increases the energy of your signal during the reception period will increase the interference that this signal will create to adjacent reception periods. Therefore, your signal to interference ratio stays the same regardless of your power. So what is the recipe here? What is our course of action? Well, our course of action will be, well, let's not signal with square pulses. That seemed like an obvious one. Let's try to devise a pulse that will actually have certain properties that will minimize the intersymbol interference, right? So I need to find out, embark on a search for the time domain versions of this SM of t such that it does not create interference in the time domain when I receive it. And to do that, we actually approach this in two steps. In the first step, we have to understand what does the spectrum of a digitally modulated signal look like. So far, if you follow what I did here, I actually looked at a single pulse. For single pulse, I know how to do Fourier transform. But when there are many, many pulses coming one after the other, I end up with digitally modulated signal for which I need to derive what the footprint of that signal looks like in a frequency domain. Because it's not only a single pulse, it's many pulses coming one after the other, modulated or whatever with the bit sequence that I'm using to modulate this pulse stream. So that's our first step. And once we understand what the spectrum of a digital modulated signal looks like, this is going to be one of the fundamental results and one of the beautiful results that I want you to take out from this class. Then we're actually going to look at how do I choose this spectrum so that I don't have interference in the frequency domain. And this will, like many other things in digital communication, was first tackled by Nyquist, and there's going to be Nyquist criterion, different than the sampling. This is going to be, I think we call it third Nyquist criterion, that will give us how do I choose my pulses so that I don't have intersignal interference. And then at the end of the journey, you're going to kind of, I know some of you already seen, we're going to come up with some pulses that we use universally in communication system. You're going to recognize them. And probably at some point up to here, you wonder why do we use raised cosine or why do we use Gaussian pulse and so on. So that's where the journey is going. So to get there, I guess one step at a time, let's see if we can derive what the spectrum of the digitally modulated signal looks like. So that's our first task. But is this clear? All right, there's a little bit of math, but this picture here, even though it's not very nice one, the best in notes you have a better drawing. My hope is I just looked at the notes and it says generate one in MATLAB, so that, but I didn't do that. But try generating one in MATLAB and convince yourself that this is the case. Make this function and then vary WCT and observe what happens. This is a very similar behavior. If you remember somewhere in probably your, I would say junior year, when you start looking at the Fourier transform, we actually fed a square wave through a low-pass filter and observed a similar behavior, right? Where it starts, your otherwise perfect square shaped pulse started rounding, and then as you started decreasing the bandwidth, it started looking more and more like something that is just a blob of energy. All right. So power spectrum. All digitally modulated signal. Here's what we're gonna look at. We're gonna look at baseband palm signal. Okay? And this guy looks like this. V of t is equal sum when n goes from minus infinity to plus infinity, an psi of t minus n t. Right? So what does this mean? It's an times psi of t, then plus an plus 1, psi of t minus 1, and so on. So these are the pulses that you're sending. You're dividing the time into increments of t. And then here's your, for example, a1 times psi of t. And then let's say this is a2 times psi of t. Let's say a3 times psi of t, and so on. Right? So you have a whole bunch of pulses, one after the other, coming as a baseband pump signal. Now, this is adequate for us to treat all the cases that we have. Why? Because if you look at baseband PAM, the bandpass PAM is the same thing, just shifted to frequency of the carrier. So if I know what the spectrum looks like here, all I need to do is shift that to the frequency of carrier in a bandpass case. How about two-dimensional signal? Well, if you think about two-dimensional signaling, it's actually two baseband PAMs. Like if you look at your QAM, you have two PAMs on orthogonal vectors, right? One of them is along the cosine and the other one is along the sine. So essentially, if I know the spectrum of this one, then I can determine the spectrum of the quadrature amplitude modulated signal as essentially sum of the spectra in the two branches. And each individual branch, I have a bandpass PAM signal. So if I treat this one, I'm covering all the cases that we considered so far. What is this AN? AN is the sequence of the magnitudes, sequence of the amplitude. Like if this is, let's say, binary PAM, how many of these I have? Two, just plus A minus A. In a 4 level, I have minus 3A, minus A, and 3A, and so on, right? So I can have a sequence here. This psi of t is our good old friend basis signal, which is 1 over square root of energy times gt of t. Gt is some pulse that I use for signaling, and I have the square root of energy downstairs because I want to make my basis vector of unit length, right? I wanted to have a unit node. So how are we going to determine, so what is our goal? Our goal is find power spectral density of V of t. Right? So I need to find out what are the sinusoidals that are building this particular waveform. Right? And how I'm going to do that? Well, we're going to take our signal V of t. We're going to find its autocorrelation function. And then when I take the Fourier transform of autocorrelation function, what do I get? Power spectral density. Remember, those two guys are our Fourier transform pair. Why am I working it this way? Can I take the Fourier transform of this directly? No, because this is a random signal, right? I have to actually, these psi's are deterministic. I know what the Fourier transform of psi is, right? Just the Fourier transform of this gt of t. But these ANs are random. These are the levels that are depending on what the particular bit stream is that I'm feeding to my transmitter. So this, I have to treat this as a random process. because A is a random, right? And for random processes, to determine what are the sinusoidals that build random process, the way how we do that, we determine autocorrelation function, and then taking the Fourier transform of that, we can get the power spectral density. So that's our journey. Let's start with the first step. So what is the first step? First step is R, the autocorrelation function of t plus tau t. This is autocorrelation function of my signal v of t is equal to expected value v of t times v of t plus tau. I'm actually here simplify it somewhat because I'm going to assume that all the signals are real, right? I'm not going to put a complex conjugate here, although nothing changes majorly. It's just that math gets a little bit more involved. So for the time being, all of these are real signals. These are pulses that are looking somewhat like this, let's say, or they're square pulse or whatever, maybe the pulse that you're using for signal. So this is what I need to determine. So if I expand, this becomes expected value of sum when n goes from minus infinity to plus infinity, just substituting what I know that v of t is, an psi of t minus nt times sum when n goes from minus infinity to plus infinity, an psi of t plus tau minus nt. Right, so that's now the same as what I have here, but expanded. Now, if I look at what is here deterministic and what is random, these psi's are deterministic. So expected value operates on a product of these two. Right? So this becomes sum when n goes from minus infinity to plus infinity, sum when n goes from minus infinity to plus infinity, expected value of an times an times psi of t minus nt times psi of t plus tau minus nt. Okay? Now this here, expected value of an times an, is a property of a source. Of the source. Let me anchor this in some example. Let's say we're looking at the binary source. Okay? Now, what does this is autocorrelation function between symbols that are separated by n minus m. Looking this symbol and that symbol over there. If I did statistical encoding, let's say Huffman encoding in all of these, what is my expected value between, what is this value? When n is equal to m, I have 1, right? Let's say I have just ones and minus ones, right? So when n is equal to m, that's a trivial case. It's always 1. But when n is different than m, if I know bit at this point, can I say something about bit that's, why? Because I did my statistical encoding, so I decorrelated everything. So if I did statistical encoding, this is binary encoder, then this is delta, right? That's property of the source. If I'm now using multi-level, from the fact that my if it's symmetric, right? PAM, meaning that your remember how it's symmetric about the origin, +1, -1, +3, -3. Then this becomes also delta, right? Because you decorrelate it through statistical encoding, then by knowing this one, you cannot say anything about the one that is offset by some amount. And that's how we design our symbols. For right now, I'm not going to invoke that. We're going to do that later. But for right now, I'm going to leave this as autocorrelation function as a property of the source. But just so that you know in the back of your mind, that at some point we actually make this delta. Make this delta, and you will see why, when we get to the end. So for right now, let's just keep this as autocorrelation function because we don't need to introduce any assumption of this at this time. So we're going to say that autocorrelation function of t, ft of t plus tau, is going to be sum when n goes from minus infinity to plus infinity, sum when n goes from minus infinity to plus infinity, r a n minus n, which is this autocorrelation function of the symbols themselves. Then psi of t minus nt, and then psi of t plus tau minus nt. Now let's simplify this a little bit. If we introduce substitution, m minus n is equal to k. Therefore, m is equal to k plus n. Then this Rv of t plus tau becomes sum. Let's see here. When n goes from minus infinity, when n goes from minus infinity to plus infinity, where is k? K goes from minus infinity to plus infinity as well. Now, this n minus m, I can actually, let me actually do this. This is n minus m. And from here, m is equal to n plus k. So this becomes now Ra of k, and then sum. Now this was with respect to n. So n goes from minus infinity to plus infinity. Now instead of m, here I can write n plus k. So this is psi of t minus nt, and then times psi of t minus nt minus kt plus tau. Right, because m is equal to n plus k. So instead of psi of t minus nt, I have n plus k. Go ahead.
How about the tau minus nt? Is that supposed to be m?
Where?
The third line?
Yes. Yeah,
Is that
This is n.
same thing above, I guess?
Yes. Yeah, of course. N, right?
But for the substitution, m supposed to be n minus k for the substitution.
Where?
Last one.
Ah, okay. All right, so this is now me messing, knowing the final result. So let's just fix it. So let's see. This is n minus m is equal to k. That one I wanted to have. So instead of n, I can write n plus k. All right, or I can write here instead of m, n minus k. All right, let's just do that. So this becomes plus k. Okay, so that's my autocorrelation function. So that's the first result. The second result is the expected value of v of t. What's the expected value of v of t? This is expected value of sum when n goes from minus infinity to plus infinity, an times psi of t minus nt. And this is equal to essentially mu times sum when n goes from minus infinity to plus infinity, psi of t minus nt, where this mu is the expected value of an, right? That's the expected value of my symbols here. But you already kind of know that this is going to end up being 0 most of the time, but in general case it doesn't happen. It's going to be n. So now we stop and say, okay, what did we learn from here?
Autocorrelation.
Well, we learned this.
Yes.
If you look at this thing here, this is not a constant. So the expected value of v of t is not a constant. Right? In general case. In general case, it's some constant times this. But if you look at this function here, this function is periodic. Do you see that? If I add t to, what's the period? Capital T. If I add or subtract t, I get the same result because this sum goes from minus infinity to plus infinity. Go ahead.
So the result of these things will be like probabilistic or deterministic? Will be
Probabilistic. We are doing everything probabilistic because, you know, this is a random process. Random process. So I have a random process that has a mean that's periodic. If you look at autocorrelation function here, the autocorrelation function is periodic as well with a period t, because I can add and subtract t here, because this is also periodic function with a period of t. So now I have a process that is not stationary, but it's close to being stationary. It's periodic. It's a mean and autocorrelation function are periodic over time. We call these processes cyclostationary. Cyclostationary. And the way how we're going to go about determining the power spectral density of the process, we're going to take this one period and shrink it. And we're going to say, okay, we're going to, instead of looking autocorrelation function that is now periodic, I'm going to look at average of the autocorrelation function over one period, and I'm going to take the Fourier transform of that.
Why do you need to shrink it?
Because otherwise, I don't know how to do it.
Or you just took the samples of the...
Look what's happening. You have a process that has an autocorrelation function that looks like this. Let me just draw it. Let's say this is tau, and this is your t. And then these are the increments of t. Within every increment of t, you have, this is, let's say, autocorrelation function. Then it kind of changes slightly, and then it changes a little bit. But then when you get to this, it is back again, right? So what is the, I know at every instant I can determine the Fourier transform of this autocorrelation function and get the power spectral density at this particular instant. But that power spectral density is also going to be periodic in time. So what I'm saying, okay, average power spectral density is, I'm going to average this over time. Right? And when I average this autocorrelation, then I get the average autocorrelation function for this period t that does not change, that is now stationary. Average autocorrelation function does not change over time.
So you need to do it for each of the one that...
For each over this period t. Because if I do it for this period t, then I get autocorrelation function that is stationary across entire t. And then when I take the Fourier transform of that, then I get a power spectral density. That's an average over time, right? But usually this t is so small that the average is good representation.
But in this case, you need to have n equals to m, or n equal, it should not be equal to m.
We're past n and m. You know, we needed n and m just to establish that this is periodic. Now I'm looking, okay, now that I know it's periodic, it's a cyclostationary process. Let me average one period so that I can get its power spectral density. Right? So let's do exactly what I just said. So I guess I kind of follow the same. So these autocorrelation functions are going to be averaged into RV, I guess, here all the time, into some autocorrelation function, RV of tau, that looks like this. So how do I do that? So our V average of tau is going to be 1 over t, integral from minus t over 2 to t over 2. RV of t plus tau dt, right? This is how I average everything, right? I take the integral and then divide by the duration of the integration there. So if I substitute what RV of t plus tau is, this becomes 1 over t, integral from minus t over 2, sum, k goes from minus infinity to plus infinity, Ra of k, and then I have sum, when n goes from minus infinity to plus infinity, psi of t minus nt, psi of t minus nt plus kt plus tau dt. And this is equal to 1 over t. This guy can go outside because it doesn't depend on t at all. So let me actually rearrange a little bit. So this becomes sum when k goes from minus infinity to plus infinity, Ra of k, and then sum when n goes from minus infinity to plus infinity, 1 over t, integral from minus t over 2 of this thing. So this is psi of t minus nt, psi of t minus nt plus kt plus tau dt. And this is equal to 1 over t, sum k goes from minus infinity to plus Ra of k. And then again, okay, so now it's here. So this becomes sum when n goes from minus infinity to plus infinity, 1 over t. Now, if I call this t minus nt x, so this becomes psi of x, and we just do that. T minus nt is equal to x. Then dt is equal to dx. And this becomes then psi of x plus kt plus tau dx. And then when t is equal to minus t over 2, then this becomes minus t over 2 minus nt to t over 2 minus nt. You understand now, because x is, when t is minus t over 2, then x is minus t over 2 minus nt. And this is when x is equal, when t is equal to t over 2, x is t over 2 minus nt. Now, let's take a look at what this sum does. This is integrating from minus infinity to plus infinity, minus nt, minus t over 2 to minus nt plus nt over 2. So here's, minus nt. You go here, and then you switch over. So this is t. Then you switch over here, and n bumps by 1. So then you integrate from here to here. This is minus n t plus t, right? And then you switch one more over. So what is it that you're integrating over here? Entire axis, right? In increments of nt. So this whole thing becomes equal to 1 over t integral sum k goes from minus infinity to plus infinity r a of k times an integral 1 over t when x goes from minus infinity to plus infinity psi of x plus kt plus tau dx. What is this? This is autocorrelation function, right? Again. But autocorrelation function of what? Of your basis vectors, of your psi of t. So this is equal to 1 over t sum when k goes from minus infinity to plus infinity r a of k and then r psi of tau plus k. So that's my average autocorrelation function, and then what the last step is to find out the Fourier transform, and I'm just going to write it, what the result is, because we're running out of time. So our power spectral density SV of f becomes Fourier transform of RB of t plus tau. And then what happens is you take this, put it in Fourier transform, and after some steps, you end up with this. 1 over t SA of f times psi of f squared, where this psi of f is the Fourier transform of psi of t, and this SA of f is 1 over t, sum when k goes from minus infinity to plus infinity r a of k times t to the minus j 2 pi f k. So this is essentially your Fourier transform of the pulse, of the basis signal. And this is the discrete Fourier transform of your symbol autocorrelation function. Okay? So this is the end result. So let me just kind of stop here and then give a little bit of explanation, and then next time we're going to look at what is the more thorough explanation of this. So what was our goal? Our goal is to determine the power spectral density of your digitally modulated signal. So if I have a signal that I digitally modulate, what does the footprint of that signal look like in a frequency domain? And it turns beautifully here that there are two effects that shape the power spectral density of the signal, and that these two effects are separate, that they are kind of separate from one from another. One effect is shape of your pulse, right? Shape of psi of t. So this is what you start with, right? And this one is easy to determine. This is something that is absolutely in our control, right? This is what we select for signal. I could have selected psi of t to look like a square pulse. Then this becomes sync. So my signal looks like sync in a frequency domain. This is the Fourier transform of the autocorrelation function of your sequence. Now, we said earlier that most of the time through our coding, we're going to make this autocorrelation function look like what? Delta pulse. So what is the what is the Fourier transform of the delta pulse? Constant. So even though this looks scary, for most part, this will actually design our systems for this to be constant. And what we learn here is a beautiful result that if you actually do your statistical encoding properly, meaning that you decorrelate your symbols and make them equiprobable and uncorrelated from one from another, then the footprint of your signal in the frequency domain depends only on your pulse selection, right? The selection of your pulse. So that means all I have to do is focus on selecting my pulse so that I minimize my intersymbol interference. So that's the result here. I know it's a little bit elaborate, but this result is worth remembering, right? It tells you what does the digitally modulated signal look like in a frequency domain. And if you forget everything else, what you should need to remember that under most common circumstances, that means you do statistical encoding, or maybe you don't do statistical encoding, but you convolve your bit sequence with a random PN sequence of the transmission to make all the bits decorrelated. What happens is the spectrum of your signal looks like the pulse that you have selected for signal, which is a remarkable result. It doesn't have to, on the outset, you don't necessarily see why it has to be that way, but it turns out it is. If you go through this market, your signal in the frequency domain looks like the pulse that you have selected for signal. So now that we know that, the next time we need to actually put some constraints on this pulse, and then what you will see is there will a whole range of pulses that will come out that will allow us to signal over band-limited channel without intersymbol interference.
Excuse me, Professor. So in the final exam, they're going to comprehensive or start from the
No, final exam, so that you can start early, is going to be chapter 7 and a little bit of chapter 8 that will come. So, starting chapter 7, this is going to be demodulation, detection, probability of error, and a little bit of material that we managed to cover. Next.
So you will cover from the still from the